Good afternoon and welcome to the North Carolina Museum of Natural Sciences Triangle SciTech Expo. My name is Greg Scupian and I'll be your host during today's program. A couple things before we get started. I just want to send a big shout out to our sponsors, the NC SciFest and the Biogen Foundation. Without them, presentations like this one wouldn't be possible. For those of you joining us on Zoom, I just want to go over a quick tutorial first. Closed captionings are available during today's program. To access those, all you have to do is click on the CC button at the bottom of your screen and then select Show Subtitle. For optimal viewing, we recommend using the speaker view in the side-by-side mode. So you can access those by clicking on speaker view or view at the top of your screen and then selecting side-by-side. You can also adjust the size of your screens by clicking and dragging on the bar there on the right side. And of course, we want to hear from you, so ask all your questions and comments in the chat, but we do request that you be a good digital citizen, keep things relevant and positive. So it is my pleasure today to introduce our speaker, Dr. Rachel Smith. Dr. Smith is the head of the Astronomy and Astrophysics Research Lab and curator of meteorites at the museum. She's also the associate professor at Appalachian State University, and she's going to take us on a virtual journey to observe stars, planets, and the space beyond. Welcome, Rachel. Thanks for joining us.
Thank you. Great to be here. All right, so I'm going to share my screen. Hi, everyone. Welcome. I'm so glad you all could come to an afternoon talk. So I am going to hide. Let me just see here. So how does this look, Greg, as far as bars and things?
It's looking good to me, Rachel.
Okay, so you don't see a gray bar anywhere?
One did just pop up.
Yeah, all right. So let me just see something real quick. There we go. Hi. Okay, so now you shouldn't see that. Right?
Those two went away, but now we have a bar right through the middle of planet Earth, and now it's gone.
Okay, good. Okay, great. So so Zoom likes to come and hijack my program, but hopefully this will be okay. So, hey everyone. And I'm going to take you on a little tour. Some of you, if you've seen some of my programs, may have recognized some of the content, but hopefully not all. And so I'm showing most of the stuff I'll show you today, with the exception of some images that will pop up in and out as I take you on this tour. All of this software here that I'm showing you, this is called OpenSpace. And it's a NASA-funded project that's led by the American Museum of Natural History, and we are partners with them. So we create programs and content and have students involved to get some really great visuals to all of you. And we also have some of these visuals showing in the lab at the museum as well here. So if you get a chance to come by, we're updating that, and we're all really excited about OpenSpace. So OpenSpace takes you from essentially Earth to the universe, to the end of the universe. And hopefully we'll have time today to go on a tour to see everything, but we'll see how the time goes. So this is Earth. We're, I think, a day before Earth Day, right? And this is also SciTech Expo. So I'm going to talk a little bit about data and also Earth and the importance of Earth and how we explore space. And with that connects us to astrobiology and how we use Earth as an analog to look for life beyond it. And I'm an observational astronomer, so I use some cool technology, and I'm gonna show you that too. And whenever you're thinking, when I show you these visuals as well, think about how do scientists see the universe? And when we start with Earth, it's kind of obvious perhaps because we live on Earth, and so we have great visuals of our own planet. And here you can see our own planet with this sky in the background, which is all correctly placed. It's part of a big database called Digital Universe that is housed and maintained by the American Museum of Natural History, who created it, and it's all available in OpenSpace, which is free software. And oh, by the way, there is a survey. I don't know if Greg mentioned it, but there is a survey. If you don't mind, after the program, taking that, it helps our project and helps the programmers to see how we're doing. So please do that at the end, and it'll be dropped in the chat if not already. Okay, so one thing that, these lines that you see here, these are orbital trails, and I'll just zoom out a second here. So I see that Zoom is popping in and out, and that's why you may see a gray bar. Greg, just let me know if it's distracting, because I can't seem to make it go away. Let me try something here. So hold a second. Oh, did it go away? I think it did.
It's reduced. Yes, it's smaller.
It's reduced. All right. Yeah, I have to figure out once if it pops up again, I'll figure that out. All right. So we are the only habitable planet in our solar system, and I will just zoom out a little bit so you can see these trails. And with OpenSpace, you can go faster than the speed of light. So here we go. We're zooming out, and here you can see the orbits of our planets. We have 8 planets. And we are in what's called the habitable zone because it's the only place in our solar system where liquid water can exist. And so here's Earth, this little blue trail right here. And all the way out is Neptune, and that's our last planet. And beyond that is the Kuiper Belt, where Pluto lives. And beyond that is the Oort cloud, probably, where all of our our long period comets live. And hold on a second, let me see, hide floating meeting controls. So there we go. I think I'm hiding them now. And beyond that is the edge of the solar system. And then, of course, and so hopefully we'll talk a little bit about that today. So when we visualize the orbits, these are shown as trails right here. We are helped with OpenSpace in visualizing these. Of course, they don't look like this. You wouldn't see a line if you flew out to space, but we can measure these orbits to a high degree of accuracy. So let's zoom back to Earth, because we don't have a huge amount of time today. And so we visualize our planet with satellites. We get updated data that pulls from a database for OpenSpace. And with Earth, it's pretty recent. It could even be today where some of the data sets are. So you'll see pretty recent clouds and weather patterns here. And of course, what makes our planet habitable, and this is, thinking about our only planet where we can have life right now that we know of, is water. And so we can, the habitable zone by definition is a planet that can maintain, or moon, that can maintain liquid water on its surface. Those bodies would be inside the habitable zone. You know what? I can't stop this window from popping up, so I'm sorry, you guys. It just keeps doing it, so I don't know. But anyway, so here we're going to zoom in and just let's see here. I will get to my first location. I made these bookmarks for us. Let's see. Oops. And again, you can do this at home if you want to download OpenSpace at openspaceproject.com. I'm sure if OpenSpace folks are here, they would drop that in the chat. And here we go. It makes a little circle for me so I can find it. So I'm going to take you to the Grand Canyon. We don't have, I want to take you from Earth to the end of the universe. We don't have a whole lot of locations we can actually go to, but I'm going to take my little marker off so you can see it. So the reason I'm going to the Grand Canyon is it's really spectacular to see, and whether you're in person or even with OpenSpace, and I'll just zoom out a little bit. It's our largest canyon on Earth, but it isn't actually the largest canyon in the solar system. And some of you may know that the largest canyon in the solar system is Valles Marineris on Mars, and we'll make a stop there as well. But let's zoom in a little. We have this thin atmosphere. I'll just stop, sorry, for a second again. See this little thin atmosphere? This is what keeps us alive, essentially. It's critically important that we have this atmosphere on Earth. And Earth maintains this atmosphere with a magnetic field, which helps protect us from the sun, which will strip away our atmosphere if we didn't have this magnetic field. One thing that's fun with OpenSpace is that you can fly around. You can go in, see everything in between. If you want to go from Earth to Mars to the cosmic microwave background, you can do that without skipping any places. You can see the stars around you. You can see the galaxies if you turn those on, and you can drive all around the universe, which makes it so cool because it's all right here in the same place in these menus. So you can, you can fly. Oh, I know I have to refocus here. So I am showing you how I drive. Right. And then I'll reposition. All right, so it's quite beautiful. This is all real data. So everything you see with OpenSpace is all real data. Even if we look at exoplanets, we know where these exoplanets are, even if we haven't gone there. And that's how scientists visualize the universe, is we have telescopes, we have remote ways of sensing, and we can tell where everything is. And so we can place these in space realistically. And so you can go to the Grand Canyon and you can fly around, and it's actually quite beautiful with OpenSpace. You can go all around Earth with OpenSpace and get all of this degree of detail. And again, we live on Earth, so we have the best detail of our own planet. So I'm going to go to one more spot on Earth because I want to take you beyond Earth, and that is Mauna Kea. And the reason we're going, I wanted to say one more thing. So actually, I'll skip this, but I was just going to say for when we think of our planet and the history of our planet and animals on this planet, there's a crater nearby called Meteor Crater that 50,000 years ago, a piece of an asteroid hit on Earth. And it's very near to the Grand Canyon. I won't actually go there. But during that time of 50,000 years ago, there were some different animals on this planet. And those would be woolly mammoths, for example, giant sloths. And these animals would have been living here in this region 50,000 years ago when an asteroid hit. And asteroids are important. We're not going to talk too much about asteroids in this program today, but they're important because they could have delivered ingredients for life as well as our oceans. So we just don't really have a full understanding of that yet. All right, so let's go to Mauna Kea, and I'm going to talk a little bit about Mauna Kea because this is where I do my observations now. I have some projects using a telescope on Mauna Kea, and I'm actually going to get pretty close, and then I'm going to wake up Hawaii here. I hope this is not too distracting with the window coming in and out. Greg, you can tell me how that looks.
It looks all right. It's there, but it's not a huge distraction.
Yeah, I don't know how to fix that. It's something to think about for next time. I'm not sure.
May I ask a question from the chat, please?
Yeah, for sure. Yeah.
Ryan was wondering what the blue line was at the top of the Earth, and I'm not sure if he's referring to the haze, or it looks like there may be some orbit lines in the distance.
I think he's probably referring to I think that's Earth's orbital trail. I have the orbits left on, so it's probably it's either Earth's orbital trail or so it's one of these lines up here, I think, right?
Possibly. Is that the atmosphere that's kind of the hazy stuff at the very edge of Earth?
Yeah, so this here, I'll say, let me hold on a second. Turn this off. So if you mean this line here, if that's what he means, or is he talking about these lines here? These are orbital trails here, most of which are the planets around us, and there may be a mission or something in there. I didn't actually turn them off. I left them in because I thought it was kind of cool to see. But most of these are planets, and perhaps the ISS. I'd have to identify each one. But this is our atmosphere right here. So I hope that answers his question.
I think it did. Thank you.
Okay, you're welcome. All right, so let's go to Mauna Kea. And Mauna Kea is probably the best location for observing on Earth. And the reason is, I'm actually going to make it a tiny bit brighter. I'm going in the right direction. Sometimes it's hard to... There we go. This is a shield volcano in Hawaii. And it's mostly dormant. We don't think it's ever going to erupt again, but there's still a small % chance that it could. This is on the big island of Hawaii, and it's about 14,000 feet up. It's a shield volcano, which is the same type of volcano that's on Mars, which is the largest planetary dormant volcano. It's inactive because Mars doesn't have tectonic activity. That volcano is called Olympus Mons, and we'll go there as well. But this is a shield volcano in Hawaii, and these are cinder cones, and it's quite spectacular to visit it. And there are 13 working observatories. It's 14,000 feet in altitude, and we go there for a few of the telescopes, we can actually go to Mauna Kea and observe at the summit. And I'm going to just zoom out a second. So we make sure we get there faster. There we go. All right. So down here, we'll get to our observatories. So we have, there's 13 of them. And this is the reason this is so great is it is high altitude. It has a huge percentage of nice weather days compared to, say, other regions. Like in Chile, it has more good weather days. And it's above most of the clouds of this marine layer. It's above a lot of the marine layer, which can really mess up your data. So you don't want to be near the clouds. So these are the Keck telescopes right here at the bottom. And this is the infrared telescope facility, which is what I use now. And I'll talk a little bit. I'll stop on Mauna Kea for a second and show you a couple of images of observing at Mauna Kea. If I can turn OpenSpace around, there we go. And you can just see it's quite stunning. It's a stunning place. You can hike up here, and I don't want to get too close because sometimes we can't zoom all the way in. That's why you see these boxes come up. But it has all of these. It's really an amazing location for astronomy as well as to visit. All right. So observing on Mauna Kea. So you get, you basically as an astronomer, you stay in one of these little houses at about 9,000 feet elevation. And there is still some plant life there. As you can see, this is the Mauna Kea silver sword, which is one of these really hardy plants that only lives on Mauna Kea. And it's actually pretty endangered. You can visit it once you go there. And there's a little enclosure here where you can visit how they're this little garden of Mauna Kea silver swords. And you just have to keep your feet clean and go in and you can see them. I stop here and talk about them because when we think of Earth and we think of different kinds of life that can survive on this planet, a plant is actually a very advanced form of life compared to, say, a microbe, which we think if we find life, it will probably be microbial if it's on Mars or, say, Europa, in the ocean of Europa, if at all. But still, there's some really extreme environments where animals and plants can subsist on Earth. And this is how the plant looks up close. It's this cute little, I really like it. It's beautiful silver color. And they live they can live a few decades. And this is the way they look when they flower. And once they flower, they die. So sometimes you see them flowering, and that'll be it for this particular Mauna Kea silver sword. But then, of course, its seeds will go to new Mauna Kea silver swords. So this is how it looks when you're going up to the summit. And it's really quite a stark landscape. And it makes perhaps one think of Mars, or I sometimes think of, could this be what it's like? If we send astronauts to Mars, it's going to be a pretty stark landscape. And we've seen images now of the rover, of the images from the rover that just landed a few months ago in Jezero Crater, and we'll take a look at that area as well today. And just there's no vegetation once you get up to a certain altitude. As far as the Mauna Kea, this is the cloud layer that you want to be above. And if you're below the clouds, then you have all of this water vapor, too much water vapor that can really get in the way of the data you want to look at for your stars. So once you get to the telescope, it looks like this. It's a 3-meter telescope. This is the dome. It is run by it is really run by NASA. It was started by NASA, and it was started by NASA to actually support the Voyager mission. And I'm going to talk about Voyager towards the end of this presentation, so I'll hold off a little bit. But the Voyager mission was launched in 1977, and these are the 2 farthest probes we've ever sent into space. And I will bring back Voyager a little bit later on when we talk about exoplanets and our radiosphere. And this was the telescope built to support that mission. But what's really cool now is it's a pretty old telescope, but it's really powerful still. It can collect a lot of light that we need from faraway stars. And we can study, it also has updated instruments. So the nice thing about ground-based astronomy, which isn't so easy for space, is you can update your instruments pretty easily. Well, not so easily, but it's possible because you're on Earth. If you have a telescope in space, you're not going to replace an entire spectrometer. You might be able to fix it, like we were able to fix Hubble, but you're not going to replace an entire telescope or an entire instrument on a telescope. So ground-based astronomy is actually really great for keeping some updated instrumentation and using our mirrors as much as possible. So this was me, in one of the recent observing runs I did. I haven't been going there the last year because of COVID, but hopefully by the fall, I'll be able to go back and we have a proposal in to continue our study now. So this is NASA's, this is in front of the sign. When you go in, this is the base of the telescope arm. So it moves, and I'll show you a picture of what it looks like, and it moves the telescope. And when you observe on the summit, you'll observe in a room just adjacent to this one. So you can be inside the dome. There's actually a person standing here who's replacing some of the helium tanks. Liquid. There's some nitrogen, there's liquid helium, there's chemicals keeping the instruments cold. because infrared astronomy has to be cold or the heat will mess up your data. So here's, this is a little dark, I know, but here's another picture just showing the telescope here for scale. I'm about 5'5", so just so you know, I'm not a giant or very tiny, but so that's kind of for scale. And inside the dome, as an astronomer, you know, people may think astronomy is very adventurous. We use all these telescopes, but the truth is that we don't go observing that often with these big telescopes. I may go twice a year and get a couple nights, and the rest of the time I'm sitting in front of my computer at home or in my lab looking at data. So being at the telescope is really exciting, and I go in and I see the telescope, and I'm at the telescope for observing, go in the dome and see what I'm kind of recenter what you're doing. I think it's very important for astronomers to go to their telescopes and as much as they can. So I just put this slide in because it is SciTech Week, the SciTech Expo, just to give you a sense of what happens in a telescope. So you have at the top, you'd have light coming in, right? This arrow coming down. So light's coming in from a star or whatever you're looking at, you're pointed at. And the light comes in and bounces around a lot, basically. That's how you could just think about these arrows as bouncing around different mirrors, and then finally getting to something called a CCD detector. And that's here in this gray area. And sorry again for this bar coming up and down. Zoom hates this. I will fix this for next time, I promise. But anyway, so you have this detector, and that detector takes a picture. And even though I'm not actually looking at images necessarily, I'm looking at spectra, and I'll show you what those look like. We convert these images of lines and shadows and lines, and we convert those to spectra. And so essentially we're collecting all of the light, it's taking a picture, and then we convert these pictures to spectra. Later on, we do that in a code. We have a whole way of converting the data. So this is how light passes through our telescope and into our instrument. And so iShell is the instrument, and IRTF can have, just like lots of telescopes can have different instruments. So you put the instrument on that you're using, and then it does what it needs to do here. And sometimes the instruments are cameras, and sometimes they're spectrometers like this one. And sometimes there are other types of instruments, just depends on what you're working on. And so that's just a little bit of a general overview. To collect the data, this is in the little office next door. We have computers. We don't look through an eyepiece. We have computers. My colleague was observing from Oahu here. They give us snacks. The IRTF telescope facility supplies you with food. They call it a night lunch. They literally give you a lunch that you can eat at night because you're up there. So it's a very nice it's a very nice system they have worked out. And here you can see there's some, this is how kind of the data look a little bit, little squares. You can see where you're looking, you can look at your star, and you're not alone, right? You have people like this person who's monitoring the weather, and really it takes a whole team to operate a big telescope. So you have people looking at weather, people looking at the instrument. We have at least usually two people up with the astronomer in non-COVID times. And then in COVID times, we have to unfortunately all observe remotely, except for the one person perhaps, or there's usually another person for safety. Two people, just the bare minimum team up there, and then we have to do the observations remotely, which isn't quite as good. But it takes a whole team. If there's a lot of fog or precipitation, the dome closes. Priority is preserving that instrument. So I do take some pictures. We take some pictures to know where we are. We can capture these pictures, and this is a forming star here. One of the stars that I'm studying, looking at the chemistry of this star. And here you can just see this black line is the telescope. It's called the guider. And these are winds blowing off of the star. And the blue is kind of colder, basically, or less intensity. And red is hotter, so it's a little like a fire. And this is the wind coming off of this forming star. And the cool thing about these stars is they're forming all around us in our galaxy and probably in other galaxies, but we only observe in our galaxy with the instruments we have. And they're analogs to our solar system. So we can try to understand the chemistry of our early solar system and of systems that will form planets eventually, like we think most stars have planets, and try to understand the chemistry around these stars. This is probably not as good a picture, but if you look closely, you might see two stars. This is a pair, a really interesting pair. It's called a binary because it's two. And this is the name of the star system, Honor 2 Iris 3. But But the cool thing about the binaries is that most stars form with pairs. And so we want to learn more about that to try to understand how these systems might be different from single stars. And it turns out our sun probably formed with a companion, but we're learning, we don't really know for sure. And so these binaries can actually help us learn a lot about chemistry of different kinds of exoplanetary systems. So this is what a spectrum looks like. It's not usually as glamorous perhaps as an image, but this is where the data are. So you could just think of it as light intensity on the y-axis, and this is wavelength. So this just tells you kind of which molecules you're looking at. And the lines coming down are basically the molecules. And I'm just showing you one little snapshot here of a spectrum. But the point here is that these are fingerprints or signatures of molecules. And the molecule in this spectrum is carbon monoxide, just like the stuff that comes out of your car. And we can understand carbon and oxygen chemistry by studying carbon monoxide. It's a really important molecule as a reservoir for carbon and oxygen. And so anyway, that's my next level. So that's just one example of a spectrum. And then I'm going to move on to the next location, which happens to be Mars. So we can go on to Mars. But that's just a little bit of the data, just to give you a sense of what I'm doing. And from here, we are going to go to Mars. Unless there are any questions about that, I can pause a second.
Yeah, we had just 2 questions about the telescope itself.
Yeah.
I'm wondering, it seems like a lot of researchers would want to get their hands on that telescope. How is time divvied up between all the people researching outer space?
Great question. These are proposals. So you write an observing proposal to observe. It's just like a proposal to get money, but we write a proposal to get observing time. And if you get the time, then you get to observe and you don't pay for the time. The only thing you have to pay for is like going to Hawaii, which actually, relatively speaking, isn't that expensive compared to an entire research project. So my research funds for myself are really to go to the telescope and then to like present at a conference or something like that and other little things. But you write a proposal, and certain telescopes are more oversubscribed, meaning you get more people proposing, and others aren't. But we have had pretty good luck with IRTF. So I've had now three funded. Every proposal's been funded, or been awarded, which is nice. And I've had 3. I've one now in the works. I skipped one semester, but that's essentially how it works. And this is true for all big telescopes. So Hubble works the same way, JWST will work that way, and all these big ground-based telescopes that are competitive work that way. So,
okay.
Yeah.
And what about somebody like myself or somebody from the general public? If we were lucky enough to go to Hawaii, could we get a tour of the telescope, or is it closed?
They give minimal tours. So at Keck, the big telescope will only give a tour to an astronomer. And you can't even bring your friends. They've told us, you can bring someone, actually. If you're an observer, they will give you a tour. You can bring someone, but you can't send someone and say, like, these are my friends, they're coming. Could you give them a tour? They don't do that. IRTF is fairly small in comparison. I don't know. What these telescopes typically do, it's a public mountain. So you can go to the mountain and they often have a door that you can open and at least see in. But to get an actual tour, the biggest observatories are Keck and Gemini. And Keck, you could only get a full tour if you are with an observer. And so that is the only way possible that I know of. They kind of limit the people. But there is an observing window you can look in, but that's not the same thing, I know. So I don't know about IRTF. I don't think they do that. But
okay.
Yeah.
Well, I'm not going to Hawaii anytime soon, so why don't you go ahead and take us to Mars?
I sure will. Well, here we are. And this is Valles Marineris. This is that huge canyon that I was telling you about. It's the Grand Canyon will be a tiny little sliver in a corner compared to Valles Marineris. It probably formed in a combination of tectonics and maybe a little bit of water flow, but not the same way as the Grand Canyon exactly. That was formed by the Colorado River. So we can do a lot of comparative planetology and with Earth and other planets, because we all form from the same stuff, right? We all formed from rocks in a spinning disk. We want to go to Mars because it's like we sometimes think of it as a sister planet, although Venus is also considered a sister planet sometimes, although we don't want to go to Venus anytime soon because it's super hot and has an enormous greenhouse effect. But Mars we are going to. We just went to. now on Mars again with the rover, and eventually hope to send astronauts. But if you really want to have some fun, take a ride through Valles Marineris. And again, this is all real data. This is data from the Mars Reconnaissance Orbiter. You see sometimes these geometric shapes. This is how the data come through. And sometimes we don't have the same resolution data for all of the locations. So as we map a planet like this, and all of the data actually I'm going to show you is from an orbiter, it's from the satellite. So we can have this amazing resolution just from a remote satellite. And but again, we don't always have the highest resolution. So that's why you have certain areas that look a little bit different. But that's just how that's just part of the data processing. So here Mars does have a thin atmosphere, but not nearly what Earth has. It has lost its atmosphere through the phenomenon of solar wind stripping. But again, this is a fun ride. You can just go through Valles Marineris, and we don't have time to do a whole lot here, but I will zoom out actually and take you to one more spot before Jezero. And when we think about, also, I'll just say, and when we get to Jezero, this becomes more apparent, is that Mars had water in the past. We know this pretty much for sure. There's a lot of evidence for it. There are channels, old outflow channels. Jezero is an old delta. And just looking for, here it is. Olympus Mons. And so we know that Mars had water in the past. And so what happened to its water? Well, it lost its atmosphere. And once it lost its atmosphere, it lost its water, because without an atmosphere, you can't hold water on a surface. And so this is this whole part about habitability. And when we think about that, where are we going to go if we ever have to leave this planet? We are the only planet right now in the habitable zone. And so maybe one day we'll be able to terraform Mars. And we'll think about that in a second, maybe a little bit more. But this is Olympus Mons. This is also a shield volcano, just like the volcano I showed you on Mauna Kea a second ago. So let me turn this little sphere off, my flag. So this is Olympus Mons. It's actually a very shallow volcano. And here you can see those strips of data again. So if you zoom into some of these, you would see higher resolution data, but this is pretty nice, I think. These are all these outflow channels. You see this, there's so many regions of Mars where you can see old river channels and water from flowing water in the past. It's possible Mars has sometimes flowing water on its surface now in a very, briefly, and then it evaporates again. There's some evidence for that, but mostly it's not a planet that can hold water on its surface. And so if we're going to live on Mars ever, we need to think about how we're going to do that. Are we going to live in a space house forever and going outside with helmets on, or are we ever going to be able to terraform this planet? And that is something we don't know nearly how to do. It may never be possible. So this is a really beautiful volcano. I think this is an amazing place to explore with OpenSpace. And here you can see the caldera at the summit. And it's a fun place to travel around if you get a chance to play around with this. So I'm going to do a quick shortcut to Jezero. This is the Perseverance rover that's now, of course, at Jezero crater. And hopefully this loads pretty fast. Let's see. It may be a little dark, so I may have to turn off. I may have to just, let's see, zoom out a little bit. All right. So as some of you know, I'm sure, there was a historic event the other day, about 2 days ago, I think, where scientists flew a helicopter. So it was the first powered flight ever on another planet, which is really spectacular. And this is, so let's just take a look around Jezero for a second. So here's Jezero, and let's travel around. You can see here, this is the old, it's an ancient river delta. And if I can get this to work, hold on. I think this is one of the most beautiful regions of Mars. It's got amazing topography here. This area here is the ancient shoreline, where they think they found evidence for these microbiolites, so these deposits that could be microbial, but of course not necessarily. So we want to explore that more. There are impact craters you see all over Mars, including at Jezero. This is a crater within a crater. And these impact craters are from asteroids, maybe a few comets, but probably mostly asteroids that impacted Mars in the past. Jezero is right around here in this, excuse me, Perseverance is landed right about here. And we can zoom down a little more, take a little roundabout way. This is this region here, I'll show you. The river channel is coming through here. You see this line, this channel down here, and it came through and then it fanned out in a delta. And this is why Jezero was picked as the destination for Perseverance, because we want to go where water existed in the past, because where there was water, there could have been life. And in case you missed it in the news, I just wanted to stop roughly where, I can't get it to the exact location, but roughly where Perseverance is, and just show this image of the helicopter that flew. This is an image from NASA, and this is a little helicopter, and it flew about 10 feet, and it's going to do about, for a few seconds, not very long, 10 seconds or something. I don't have the exact number, but a pretty short flight to test it. But just appreciating the engineering accomplishment this is, because we're essentially in a nearly airless atmosphere compared to Earth, and no one knew how to power a flight without air, right? Because we need air, of course, to power our helicopters and power our planes. And so they were able to, engineers at JPL, the Jet Propulsion Lab, stuck this on Perseverance kind of late in the game. It was a high risk, high reward addition to the rover. So if it worked, it was going to be amazing. And if it failed, it wasn't going to be a huge loss. But it actually did work, and is a pretty amazing accomplishment for the scientific and engineering community. And now we have this helicopter that's going to be able to fly around and hopefully get a different perspective. The engineers, Perseverance, I believe, drove, sent the signals to the helicopter to fly, and up it went and down it went. There's a video you could go to where where Ingenuity is flying. So I just thought that was really, really cool. And there's actually, interestingly, I heard that there's a little piece of cloth from the original part of the original Wright brothers plane that they stuck on Ingenuity, because it hasn't been that long, right? On order like a century since the Wright brothers. So now we have a helicopter flying on Mars, and that's pretty amazing. So I was talking a little bit about terraforming, and we think a little bit about, can we ever transform this planet? Can we ever can we ever live on this planet? And I like this image here of this hypothesized, possibly future Martian in an ocean on Mars, dropping their suit and going into the ocean. And maybe one day in a fanciful future, this could possibly happen. But we're not obviously 100% sure if that could ever happen. So talking a little bit more about astrobiology, I just want to see, so it's 2:38. I can go to probably one moon, and I'm going to choose, we're going to go to Europa, because for astrobiology, Europa is probably the prime target that we want to focus on next. And there is a mission now going to Europa in this decade, most likely, called Europa Clipper. And what makes Europa, this is a moon of Jupiter, and what makes Europa, there's Jupiter, we'll just fly right by it. What makes, or actually they'll stay in the background in this case. But what makes Europa unique is that this is a moon that is smaller than our moon in diameter, and yet has more water likely than on the Earth itself. So the Earth is actually a pretty dry planet. It's only about 0.6% mass of water, even though 75% is covered. 75% of the surface is covered, but Europa could have an under ice ocean that is it has more volume than the entire Earth. And with that, what that means is there could be a whole community down there, possibly microbes, we don't know, but kept warm by Jupiter's pulling on the moon, this tidal flexing of Jupiter. These striations you see, these are cracks in the ice, and the brine or the salty water from the ocean comes up and percolates through the surface and makes these cracks. And so we can see these cracks in Europa, and it's a fascinating moon. And we're going to send Europa Clipper, probably not to probe and drill down yet because we don't really know how to do that, but to orbit and get more data. And so we know there's water on Europa, and this is a prime target for looking for life beyond our planet. Next, I'm going to, since we don't have a endless time, unfortunately, we're going to turn on, I'm going to go to OpenSpace and turn on the exoplanets. I'm going to zoom out a little bit. So I'm going to just show a few of the exoplanets. These are the, let's see. These are the planets that we have Kepler, which is, these are just a few of the exoplanets that have been discovered. And these are the locations of the exoplanets. So let's focus back on Earth for a second. It is Earth Day after all, tomorrow. Okay, so here you can see, this is our solar system. And let's zoom back to Earth for a second. So we can go back and forth with our virtual spaceship here. These circles are the locations of the exoplanets. We've gone to very few exoplanets. We haven't gone to any exoplanets. I meant to say we've only imaged a few exoplanets, and they look like fuzzy balls in the, fuzzy blobs. We can't get anything up close like a surface we have in our solar system. And we certainly can't visit with a probe even now, or even our fastest spacecraft, Voyager, would take 70,000 years to get to the nearest exoplanet. So we only have this remote sensing ability to see these exoplanets. And yet we are pretty certain, there are thousands of exoplanets out there. We've discovered a few thousand, but there are probably billions and possibly billions of Earth-like exoplanets. And what that means is that we have neighbors that could be very much like our own planet. And this brings in astrobiology of what does that mean for life out there? We have no sign of life from another world. And yet it makes us wonder, because all of these exoplanets are out here. And these are our closest neighbors. These are the empty houses in our neighborhood. You knock on the door, nobody's home. So we don't know of any life in any of these systems. And yet we can imagine the life. And this is just one artistic rendering of an exoplanet that was made. And they're based on real data. So in this case, this would be a terrestrial world that's in the habitable zone. So we know scientists can determine through detection methods, and I'll talk for just a second on that in a minute, but that these are terrestrial planets. We know that, meaning they have a rocky surface. We know that by the size of the planet, and we know the kind of star it orbits. So we can say, okay, this is a certain size star. We know where the habitable zone is from that star. And then we can say this is this type of planet in or out of the habitable zone. And so in this case, we'd have a terrestrial planet in the habitable zone. So we can imagine, and artistic renderings, just imagine the surfaces, and maybe one day we'll get there. So this is unfortunately a little dark, I know, but this is Luke Skywalker on Tatooine. And I show this because there are two suns here. And back in the late 70s, when we saw this film, perhaps, or, if you saw it later, this was science fiction, right? Is that two suns seemed way out there, crazy galaxy far, far away. But actually, this is not in a galaxy far, far away. This is in our galaxy that two suns is very common. And so now we've learned from the Kepler mission that multiple stars supporting planets is very common. And so we're learning about all of these diverse systems out there. This is an image of the Kepler mission. It is now retired, but Kepler has discovered the most exoplanets of any mission. And how has it done that? And there's just one picture I'm showing you this. This is called the transit method. And essentially, when I was showing you a spectrum, I was also showing you brightness or light here. And the way this works is Kepler was designed to discover Earth-like planets, small planets. And it was designed to do this through this transit method. And that means that as the planet orbits, goes in front of its star, the light from the star takes a dip here. And you can get a lot of information from this dip. You can get the size of the planet and the distance from the planet, the distance from the star through analyzing the photometry, the spectrum here. And through transit detection, Kepler has discovered thousands of exoplanets, many of which are Earth-like. It's not the only detection method, but it is the most successful now of finding the most exoplanets, at least to date. There are other new missions out there that are using astrometry and other methods. But transit detection is able to find small planets that are like Earth, and has discovered many of the planets you see here in OpenSpace. So these, so when I showed you the Kepler data set, these yellow exoplanets, these are right here. This is the Kepler data set here, and this is from that mission, all of these exoplanets. And another thing scientists can do with data is they can extrapolate. And so that means that if we have this many exoplanets here in this part of the galaxy, we probably have this many more beyond. And so we think it's been analyzed that with using Kepler data that we probably have we could have billions of Earth-like exoplanets in the galaxy. And then we start thinking, okay, well, what does that mean for astrobiology? And that brings in this mission Voyager again. And I love this mission for lots of reasons. And again, this is the mission that was supported by the telescope that I use now. So it has this really nice historic connection. But Voyager was sent in the 1970s, and 1977 was the first launch. And there are two probes, and it's now the farthest we've ever sent any probe into space. And it was designed to study the giant planets and then go beyond. And it's going 1 million miles a day. And even at this speed, it would still take 70,000 years to get to Alpha Centauri, which is our nearest neighbor. And of course, we can't even send astronauts that fast at all. We are way limited on our speed. So we have to work on technology to get far. But I put a picture up. Many of you know this is Carl Sagan, and he was heavily involved in Voyager in a couple of ways. And one particular way was that's really cool for astrobiology is the golden record. These are records. These are actual records, though not quite like the records you may know of, which only play music. These are metal records that were stuck on. This is the front and the back that were stuck on each of the probes. And the records have the sights and sounds of Earth digitized on the record itself. And they also have indications of our presence, like here's where we are in the galaxy through pulsar location. This is a transition of hydrogen to show that we are intelligent, so to speak, right? That we know stuff, and this is not random. And there are directions on how to play it. And Carl Sagan put the records on Voyager in the possible chance that they'd be picked up by extraterrestrials, intelligent extraterrestrials, which would likely be much more advanced than us and likely find them way beyond our longevity on this planet, even possibly beyond the longevity of the sun. And so this was just a relic of Earth, a time capsule to make sure, he thought it was so important to make sure our presence was known, even if we never would have a response, which I just think is so cool. And the other thing that he did, and this is in honor of Earth Day again, is he turned Voyager around. I think it was around Saturn, where he said, let's turn Voyager around to take a picture of Earth. And doing that was a request. He had to get NASA to agree to this, and because it's expensive to turn your spacecraft around. And he ended up getting this picture of Earth. This is Earth, this little dot. And this is what it looked like. It was essentially a sunbeam. And this was Earth. And this inspired his poem called The Pale Blue Dot. And if you've never heard this, I encourage you to Google it, maybe in honor of Earth Day, The Pale Blue Dot by Carl Sagan. And it's just this kind of perspective of how we should see ourselves and the importance of ourselves and having the humility we might consider having and treating each other differently and treating our planet differently, because this is what we are. We are a tiny little pixel in this giant expanse. And if we don't protect this pixel, protect our planet, this is us, this tiny little dot, then we have nowhere else to go. There is no one out there to save us. And so he talks about this. He's so poetic. I couldn't do it justice. So I encourage you to Google this. And the last thing I'm just going to say in this kind of idea of extraterrestrials and making contact is just turning on, I'll leave it here. I know we're running a little low on time. And you can ask me questions also, is that I'm just going to turn on the radiosphere, because this is as far as we've ever sent signals out to space. And it's only 100 light years. And here it is. So if we zoom this out, this grid is our radiosphere. So in our entire galaxy, we have only sent signals through radio and television for about 100 years. It's roughly 100 light years. That means that it took 100 years to get these signals out this far. Now, the span of our galaxy is 100,000 light years across, right? So that means if there are extraterrestrials, even say 10,000 light years, so just not that far away, it would take 10,000 years to get a signal there through this by the speed of light, or even this radiation, which again would then dissipate and be weaker. And then if it's farther, it would take much longer. And then of course, if we want to signal back, it would take double that time to get it back. So we have to just think about why we might not have a signal. It could be that intelligent life destroys themselves, or it could be that they're so far away and that I'll zoom out a little bit, and that we just have to wait. So this is our galaxy, and that's our radiosphere. So maybe that puts a little in perspective. That little blue dot, that's how far we've sent electromagnetic radiation. And this is just our galaxy, one of several hundred billion, or it's like 400 billion, say. So maybe that kind of puts a little in perspective. And then, are there any questions, by the way? I'll go out to the cosmic microwave background as promised.
Yeah, we have a couple of questions. Before I get to those questions, I want to remind our viewers, if you want to help the folks at OpenSpace, please complete the survey. We're going to drop that link in the chat again. I am blown away by this software. I'm somebody that look at Google Earth for hours. I definitely need to get this on my computer.
Yeah, I'm a fan of OpenSpace for its Google Earth, but the thing about OpenSpace is it's got everything in one package. So you can do this globe browsing. This is the cosmic microwave background, by the way. So this is 13.77 billion light years beyond Earth. I just zoomed out there in a few seconds. So you can go all the way out there. And if you go beyond that, it's artificial, of course, because we don't know what's out here. Is there a multiverse? Who knows? We don't know. But I'll zoom back in a little bit to perhaps more relatability. These are galaxies here, groups of galaxies, and zooming back in. But yeah, the software is amazing. It's a lot of fun to use and create programs with, and I hope it was fun to see.
So Rachel, we had a quick question. Could you use OpenSpace to take a virtual trip to the sun?
Right. There's not a whole lot on the sun right now. It's mostly just a ball of light, but that is in progress to get data sets. You could go to the sun, so I could take you to the sun, but it will just be a ball of light. It won't be like a lot of data. So there's probably no reason to really go there, but you can do that.
And then we had two questions about the JWST.
Yeah.
Carrie asked, would your research ever necessitate the use of the JWST? And if so, what would that mean for your research?
Yeah, that's a great question. So I'd have to come up with a project, and I have some friends at JWST who have encouraged me to submit proposals and stuff. But yeah, it's the same proposal process. It would mean that, so if I came up with a new project, first of all, I have a mountain of data I have to get to on my current project. So there's so many ideas I would love to do. To be honest, as a scientist, there's never enough time. So I would love to come up with a project for JWST. And that would mean I would have new amazing data for whatever I was thinking about studying. So probably something with protoplanetary disks like I do now. It would definitely be with that stage of evolution. So I'm interested in the protoplanetary, so the disk, the gas, all that stuff before planets form.
And then our last question, we have 2 minutes left.
All right.
What is your opinion of life on other planets? You showed us all those exoplanets, and you talked to us a little bit about the probabilities. Is intelligent life out there?
I think there's, so my opinion, which is worth whatever you feel it's worth, is nothing, perhaps, is that there is life out there, but I don't think it's and by intelligent, we mean, we're talking about life that can communicate off of its planet, not like my donkey is intelligent. We're not talking about that because he doesn't have a telescope. So it's about intelligent, quote unquote, means communicating off the planet. I think I'm not the only one who thinks this, but if there is intelligent life, it's got to be more advanced than us because they've had a few billions of years head start on Earth, and we are 100 years into technology. I don't think it's close by, and I think, unfortunately, what resonates with me is what Carl Sagan has said is that space is vast and the stars are far apart. That's a direct quote from something he said. And that just means that there's so much space that we will, I believe there's life out there, but that is based on not any evidence. I just think there's so much out there that there should be life, but it's also so far away that the reality of meeting that life seems very, very remote. I hope so one day. I really do. I hope we develop the technology to travel to the stars and be able to experience more. I'm an adventurer. I would love to do it if I could.
Well, that's a great way to end our program today. Dr. Smith, thank you so much for taking us a virtual tour of a solar system. And thanks to all of our viewers at home. We still have 3 more days of programs. Check out the schedule that we dropped the link to in the chat. We hope to see you at some other programs this week. Y'all have a nice day.
Thank you so much. Have a great day, everyone. Bye.
Bye.